All right, hello. So, kind of picking up where we left off with this baseball example, um, we kind of wrote out our kind of like theoretical model. So, in terms of a intercept, a slope times our predictor plus some error, we said for now we're going to ignore the error a little bit and focus on kind of the fitted line part. And so now what we want to do is we want to find some estimates for these two numbers, beta naught and beta 1, from the data that we actually collected on our 30 baseball teams from that 2011 season. And so we want to determine what is kind of the best fitted intercept and the best fitted slope. And so we're going to try to build up these ideas a little bit intuitively. And so in order to discuss that, we're first going to define fitted values. And so all these are our predicted values of our response. So in this case, the runs, um, based on the regression model. And so we're going to denote these as y with a little kind of hat on its head to denote that they're predicted based on our model. We're also going to define residuals, which in a kind of math notation is just our observed response minus what's predicted based on our model. And so in words, residuals are really kind of like deviations of what was observed from what's predicted with our model. And so when we find, you could kind of see the best fitted line plotted in this plot below. And so that line is calculated to minimize a certain quantity. And so by far the most common quantity that we want to minimize is called the sum of squared residuals. And so keep in mind that each observation is going to have its own residual. And so this observation will have a residual. So will this one, so will that one. And so what we want to do is find the line that's going to minimize kind of adding up all of those residuals squared. And so finding this regression line to minimize this particular quantity has some nice theoretical properties. But because this is applied regression analysis, not theoretical regression analysis, we're not really going to delve into that too much more than just some intuitive reasoning. And so really what we're minimizing is the residual from the first observation squared plus the residual from the second observation squared. And then we're going to go all the way down the line and suppose that we have n observations, add up all those together, and we want to find the line that makes this number as small as possible. And so this is really our sum of squared residuals. All right, so if we do that and we find the line that makes that number as small as possible, it has a particular name, and it's called least squares regression. And so this is just the line fitted to data that has the smallest possible sum of squared residuals for that data set. Okay, again, we're not delving into actually finding this any farther, but if you've had calculus before, you might imagine taking a derivative of a certain function and then minimizing that to find your best fitted intercept and slope. Okay, and so again, since we're not kind of finding this by hand, we just want to know kind of conceptually what's going on, but we're always actually going to find the fitted intercept and the fitted slope using R in RStudio. And so you'll get a chance to do that a little bit in the next kind of your turn section where you'll get some practice doing that. But for now, you could see the fitted regression line plotted here. So this is the line that minimizes the sum of squared residuals. And so what that really means is that any other line would have a larger sum of squared residuals. The output down here, for now we're ignoring that, we're ignoring that, we're ignoring that. That will pop back up when we talk more about inference. But for now, you'll get kind of similar output in R where we've got our estimated intercept. And so that is the value where this line would cross over the y-axis. And so we're x equals 0, so it would be way down at negative 642. And our estimated slope, which kind of represents, okay, if we increase batting average by 1, how much is runs scored going to go up or down? In this case, since it's 52.42, it means that on average, the run scored would go up by 52 runs. And so we could use these quantities to kind of write our fitted model, and we'll talk more about those interpretations in a bit. But for now, we've got our predicted response, so y hat is the predicted number of runs scored based on our model. That's going to be I suppose I'll use an estimated intercept plus an estimated slope times our predictor. And so in this particular case, what we estimated the intercept to be based on this least squares regression line is negative 642.8. We estimated the slope, which is in this second row, to be 52.42. That's denoted by the name of the predictor. The intercept is denoted in the row that's just called intercept, so that's nice and easy, times x. And so x is the batting average, just like it's been this whole time. And then y hat is predicted runs. Okay. And so we'll kind of leave the theory at this point for now, and in the upcoming videos we'll talk a lot more about the interpretations, so interpreting the residuals a little bit more specifically. We'll talk about interpreting a correlation coefficient, and we'll talk more about interpreting these two numbers, our intercept and our slope.